Hi AP Calculus students. Today, after we do our speed meeting, so we're wrapping up section 3.7, which deals with applied work in optimization, we're going to get to section 3.8 in our textbook, which deals with a topic known as Newton's method. So as a clarifying statement, before we get started with this section, one thing that I want to point out is that Newton's method is no longer explicitly covered on the AP Calculus exam. So up until about 2010, this was a pretty prevalent topic on the AP exam, and it usually had at least 1 to 2 multiple choice questions and had appeared previously in work that could be done in the free response. Then the AP exam has gradually shifted focus to emphasize other topics. So this is a technique that we'll discuss about approximation. And the kind of approximation work that you'll see on the AP exam tends to be the linear approximation or the tangent line work. I think that this is a really useful topic to still investigate. Although we really want to be prepared for the AP exam, it doesn't necessarily dictate all of the content that we're going to cover. I want you to see this material for the reason that you'll likely encounter it if you take calculus again in college, and also because it gets you into a mindset of iterative thinking that's really useful in different engineering fields. And so I'll talk about why that's the case a little bit as we go through these problems. These notes and this section are going to go by quickly. There's only 2 examples in the notes, and you only have 1 through 11 odd for the homework in this section. So it's pretty brief. So let's go ahead and read through the notes that we have here together. The first thing it says is that in AP Calc, we've used the method of tangent line approximations to come up with specific estimates for values where we know a related function, and then we can predict something that is close by, so in the neighborhood of that value. So as I mentioned before, tonight's homework is going to get us into a different type of approximation. And this is one that allows you to estimate zeros of equations and also to come up with solutions to specific polynomial or trigonometric or rational or radical equations. So we're going to start off with a pretty simple equation. We want to check out x squared minus 7 is equal to 0. And it asks us in the notes, how could you identify the values of x that make this equation true? So you have a description of what you'd probably do. Most likely you'd add over the value of 7 and then take the square root. So if you imagine back in Algebra 2, what you were doing here with this kind of equation is adding over that 7. We'd say x squared is 7. We'd take the square root of both sides. We would say x is equal to plus or minus the square root of 7. And then we would go to our calculator and punch in the square root of 7. But what you want to take a look at in this sentence is where it says, one thing we've discussed frequently in AP Calculus is the idea of how we can transition our math abilities from being calculator users to calculator engineers. So if you think about your calculator, you can go to it and punch in this value, and it spits back the square root of 7 to you in nice decimal approximation form. But what we want to consider is, how is our calculator coming up with that estimate? Where does it get that decimal approximation from? Does it just have a list of all possible square roots from 1 through infinity, and then it looks up those square roots and reports them back? Or is it doing something that involves computation? So the technique that your calculator uses is actually a version of Newton's method, which is the technique we're going to learn today. Also, anytime we go to our solver function on the calculator and we plug in a value and then we do the alpha solve, your calculator is performing this operation. So what I want you guys to be able to do in the future, if you have an interest in engineering or computer science, is to program your own calculator or program the computer that you work with, your desktop or laptop computer. And so if you want to design a program that does computational work, you would be inputting commands into your computer that run operations like these. And so this is what we call an iterative process, which means we make a guess and then we get a result. And then we use that result to make a better guess, and then we get another result. And then we use that result to get a better guess until we have a guess that we think is good enough. So for this problem, we're dealing with x squared minus 7 being equal to 0. Anytime you use this technique, you need an initial guess for what you think could work. Now for us, we know that 7 is a number between 4 and 9, so it's kind of sitting between 2 perfect squares. So that means its square root needs to be in between 2 and 3, because the square root of 4 is 2, square root of 9 is 3. So it doesn't really matter if you wanted to start with 2 or with 3, but I'm just going to say for the purposes of this example that our initial guess is going to be 3. So to use Newton's method, You start off with one guess, and then your goal is to get a better guess. So what you want to do is take your value that you've guessed, in this case 3, and you plug it into this formula. So we're getting a new value of x, and it's going to be 3 minus whatever f of 3 is over f prime of 3. So for us, this is going to be 3 minus. Our original problem was x squared minus 7. So up top here, we're going to have 3 squared minus 7. So if that is our original equation, the derivative of that equation is 2x. So down the bottom, we have a derivative, and we're evaluating it at our guess. So in this case, that's going to be 2 times 3. So this result will be, our original piece is 3. And then we've got minus, up top here, 3 squared is 9. 9 minus 7 is going to be 2. And then down in the bottom, we've got a 6. So we've got 3 minus 2/6. Now this is going to be a decimal value if we plug this into our calculator. And so let's go ahead and round it to 3 decimal places. So we get 2.667. So if you want to think through this as an iterative process, we started off, our first guess, we'll call that guess number 1, we said was 3. We plug it into the formula for Newton's method, and we get out 2.667. Then all we have to do is repeat that process, and we're going to get a better guess. So this was our first round. So then we can say round 2 is going to be 2.667 minus, now we've got 2.667 squared minus 7. So we're just plugging it in for the x here. And down on the bottom, we've got 2 times 2.667. So we just want to go ahead and plug that whole thing into our calculator. I'm going to do the fractional part first. So 2.667 squared minus 7, and then I divide that by 2 times 2.667. And then I've got 2.667 minus that whole thing. And I get a value of 2.646. So my second round, I took the guess that I got before, so 2.667, and I get out 2.646. Then I can do the whole thing over again. So my third option, I'm going to take 2.646, and I'm plugging first in up top to 2.646 squared minus 7 divided by 2 times 2.646. And again, I'm going to come back to the calculator. I'll do the fractional part first. 2.646 squared minus 7. Divide that by 2 times 2.646. And then I do 2.646 minus that expression. And I come up with 2.646 again. So third guess, I used 2.646, and I got out 2.646 again. So this is good news. Anytime you get the same answer twice in this process, or you get an answer that's really close, so within 0.001 of your previous answer, you know that you've gotten close to the actual value. Now we can go ahead and use our graphing calculator or any calculator, and let's go ahead and actually take the square root of 7. If you take the square root of 7 to 3 decimal places in your calculator, this is what you should get out. So that is how your calculator does the approximation for any kind of square root, cubic root, quartic root, or any kind of equation that you ask it to solve with the solving tool. Now, if you go to page 230 in your textbook, you'll see that they use a slightly more detailed accounting in this table that they have, where they write down the values for x and f of x and f prime of x, so that way you see all of the values as you're going along. But again, your goal here is you're not actually doing any square root work. You are just making approximations by taking derivatives, fractions, adding and subtracting. And so this is how our computers do computational work at a basic level for us, and for some pretty complex functions as well. So we're going to take a look at one more slightly more involved function together, so one whose derivative has a little bit more going on. And then other than that, you really have everything you need for doing Newton's method on your own. So you have an equation, you make a best guess, and it doesn't really matter if your guess is all that good to begin with, because as soon as you plug your work into this equation, from one original guess, you're going to start getting quite a bit closer after 2 or 3 rounds to the actual value. So go ahead and open up the next video so that way you can see the fully worked second example, and then you'll have all of the notes that you need for your Newton's method homework.